Hello and welcome to Chapter 2. So this chapter is the foundation of our guide to the sky. So it says it's a user guide. That should not be interpreted as being a star map or a star chart. You do have those in Appendix B of your textbook, and of course there's a lot of resources on the web too. But in this chapter, really what we're doing is we're defining all of the basics like stars, planets, constellations, how stars get their names, the color, or not color, brightness of a star. So all of those things are what we're going to look at here. So we're also going to be talking about the Earth's rotation, its revolution as well, its orbit. So also seasons, how seasons change, but we'll look at tides in the next chapter. And then, of course, we'll look a little bit about how astronomical cycles affect Earth's climate. But I do want to point out, I don't want to forget to tell you this. So regarding the Earth's climate, so we're going to look at the astronomical cycles that affect the Earth's climate, and that's all we're going to look at. We will not get into a discussion of global warming and how our own actions affect that. However, if you are interested in that, please, by all means, read that chapter in your free astronomy textbook, the one that's posted on Canvas as a PDF. It does have a really good section that talks about greenhouse gases and carbon dioxide, things along those lines. That falls more under environmental sciences. The free textbook does include it, though, and it talks about the origins of life on Earth and things like that. So it's a nice read, so you are encouraged to take a look at it, but we're not going to cover it in the actual lecture, though. So stars and constellations are the key component of astronomy, of course, and so constellations in ancient times. So I should have wrote down here. Let me write ancient times here so that you'll remember that. You want to make a note of that on your slides too. So in ancient times, constellations were groups. I didn't mean to cross that out. Constellations in ancient times were groups of the brightest stars, and that appeared to form groups, and that's a key word, appeared, because it was different to everybody. The Babylonians were the first ones to start talking about constellations and grouping them together. The Greeks had a different way of or different view, and constantly grouped them differently. So every group, every area of people, every country, or every, not even, it didn't even have to be that wide. It could have been various groups within countries. They, when they were interested in observing the sky, basically wherever you were on the planet, you could have came up with constellations and named them whatever you wanted to. So it was very loosely done. It was very loosely done, but the key or common part, all of it in general, was that in ancient times, the skies represented, or these constellations represented, heroes, people that were of importance to a particular culture. Sometimes we call them today mythological figures, but back then they didn't really think there were any myths about it. They were pretty serious about these hero stories, and where the mythology, or what we call mythology today, they in ancient times, like Zeus and things, all the mythological figures were actually gods, and or people of great power, and in some of those, I shouldn't say people of great power, gods or like a constellation was an object at that time, an object of great power. So what they thought, though, was that the position of the constellations in the sky held a story that they passed down from generation to generation, and it did go over thousands and thousands of years. But these stories, though, were always grounded in how the culture or the people appeased the god of Zeus or whatever god they were was in their night sky, And the ancient people thought that the planets and constellations and bright stars conferred a lot of power on kingdoms or kings and their nations. And that was back in the Babylonian days of Babylon, and the Babylonians really were the ones that came up with that idea. And then the Greeks were the ones that actually took that much further and said that the planets affect each individual. It's not just kings and their nations and the nation as a whole, but it's actually individuals that are affected by the planets and the motions of the planets and things along those lines. And that actually formed the basis of astrology. And that's actually what we're going to end our lecture with today. So really to understand the connection of astrology and astronomy back in the ancient days. Today there is no connection, but we'll get into that too. But anyway, the constellations in the old days or in ancient times represented heroes, mythological things that we call mythological figures today. Often they were gods. And with all of these representations came stories, and stories of maybe salvation, or stories of great triumph, things like that were handed down over the generations. But today, well, actually, before we move on to that, here's some pictures of ancient times. So I would say the first picture is more of a representation. That's our current sky. And part of the thing that we have today, this one would show Sagittarius and Scorpio. So they're the actual horoscopes or signs of the horoscope that we know now. And back in the old days, or thousands of years ago, they were still mythical heroes or monsters even. And so that's what that's their position in the sky. But then when they wanted to chart the sky or have a star guide or a star chart, this one this one here is obviously the night sky or the current sky, the same sky we all look at. But this one right here is actually an old star guide or old star chart. Today's star guides and star charts that you'll see in Appendix B don't look like this anymore. They pretty much look like the sky, and they have and they just connect or find like the Big Dipper, Little Dipper, etc. But in the ancient times, they actually had parchment paper, and on that paper they drew their representations, their gods, or how they interpreted the sky. And this little Billy box right here is actually pointing to this line, and it separates out the constellation Pegasus from Andromeda. And so they had to have a little boundary there dividing them out. And everyone's representation, whether it was the Babylonians, the Greeks, the Italians, it didn't matter who, they all had their own interpretation of the sky, and they had these loosely defined boundaries. So it's kind of like if you live in New Jersey and you have a map of New Jersey, and but then you travel out to California, and 3 different people give you a map of California, and it's all different, and you wouldn't be able to find your way around. So that's basically what this was. It was kind of like you're from one location, you may be from New Jersey, and you may have an idea of what California looks like, and then when you get there, you get 3 different maps or 3 different representations, and none of them are really helpful to you. So that's basically what the ancient times were like. So all these boundaries, so I keep saying ancient times, it lasted very long. So that ancient timeline, or that ancient time, we're talking about thousands of years ago, but it lasted all the way up to 1928. So they're not really that ancient, when we consider how recent they were actually used. So what happened though after 1928? Late 1928, the International Astronomical Union basically decided that these fuzzy boundaries or fuzzy borders weren't helping anyone. So they came up with a new representation, or a definitive version of the night sky that astronomers all around the world could use. So when astronomers in Greece are collaborating with astronomers in America and or any country anywhere, they're all going to talk about the same thing. So now we all have that universal map, and just like today, we can go out to California and ask 3 people for a map, and they'll give us the same thing, and fairly the same. I mean, they obviously different publishers will have, make a different size maybe, but we can be sure that Santa Monica Boulevard is going to be in the same spot and relative to the same streets on every single map. And that's really what today's constellations are. They're well-defined regions in the sky. They're no longer groupings that are loosely bound or based on perception of the brightest stars. Instead, they're well-defined regions on the sky, and they have nothing to do with the presence or absence of bright stars in those regions. And there's 88 constellations fill the entire sky. The constellations do have stars in them, but they're not necessarily the brightest in the sky. Maybe each constellation has a star that's brighter than the others in the constellation, but not necessarily the brightest in that region of the sky. So the stars in the sky, though, when we look up at the sky in general, not just at constellation stars, when we look at the sky in general, all of the stars appear to be close to one another. It just basically looks like, when we look at the night sky, if we took this blue box up here to be the sky, we can just put all these dots around here, and it looks like they're all close to one another, and it looks like they're all on a flat sheet of paper, and we have this little shooting star right there. So it kind of looks like we have all these little dots up there, and they all look like they're in the same region or the same sky, obviously. But what we're missing out on is that the naked eye can only see so far, and the best of the best telescopes also can only see so far. We don't have anything that can see into infinity. We just know infinity exists, and that we're limited to how good our telescopes can be or how perfect our eyesight may be. So looking at the sky in this fashion and thinking of it as all the stars are in the same plane, that's called the projection effect. So the projection effect, we have another slide coming up on that, but the projection effect basically is that all the stars look like they're projected on a screen. When we look at the sky, we can't perceive the depth. Like if we drew a little box here and we can draw it in. I'm not a very good drawer. I'm not a very good artist here, but trying to draw that in 3 dimensions or 3 dimensions here, we can see that this right here is in front of this one, or that this one there's some depth to it right there. But when we look at the sky up here, we can't perceive that depth. So everything just looks like it's projected on a screen that's in outer space. So that's the projection effect. And but in reality, the stars may be located at very different distances from the Earth. So this one's reality here. So the projection effect is apparent. It's not the real deal. It just looks like all the stars are close to each other and all in the same plane, but in reality they're located at very different distances from the Earth. So here's another representation of that projection theory. So we're down here on the Earth. We're down here on Earth right here, and then the sky can be thought of as this little screen or a big giant screen, and we can see all these little dots up here. We can project, we can kind of say, well, this one looks higher up in the sky than this one, and this one looks higher in the sky than that one. And if we drew, if we were looking at it, if another person was standing down here, we can say, well, one looks farther, east, and the others look farther west. This one looks farther north. This one's a little south. We can kind of say that, but we're still not getting a depth, though. We still see no depth. On this slide here, we still see no depth. We can't tell how deep they go. And the same thing often happens with telescopes. We can't see how deep they are. And so that again is still the projection effect there. But we'll get a little into the depth part and a little later when we measure distance. So continuing on with our discussion of constellations now, not just how they appear in the sky, we see that here's some of the easily recognizable constellations. And remember, there's 88 of them again. And each constellation does have stars in it. And the ones that are shown here, we're showing the brightest stars in that constellation. And that's what's important, because if we took a look over here at Betelgeuse and Rigel, they're really bright. And then we see the one over here, Aldebaran right here in the Taurus constellation, and then we see Sirius. Well, Sirius is actually the brightest of all the stars here. That's the brightest star in the sky. And then Polaris, everybody thinks here's Polaris down here. Everybody thinks Polaris is the brightest one, but it's not. It's actually the 50th brightest. So Sirius is the number one, and Polaris is the 50th brightest star. And but we see though that each of these constellations, here's one, Cygnus right here, that doesn't have a star that stands out as any brighter than any others. This Lyra down here has Vega. Virgo has Spica in it. Big Dipper doesn't have one. Big Dipper is pretty much all the same brightness, but the Little Dipper is the one with Polaris in it, and it helps us to track. Once we find Polaris, we can find the Big Dipper. But most people find the Big Dipper first. They find that easier to locate, and then once you find that pointing star there, you can just trace it back up over here to find Polaris. But the gist over here, though, is again that constellations are clearly defined patterns of stars or grouping of stars. They don't necessarily have to have a really bright star in it. In the case of this one right here, they're all about equally as bright. But then all the other ones on this sheet right here or this slide do have a brighter star. And those designations come from astrologer, I think it's Johann, last name is Bayer. His designation, though, was instead of just saying Betelgeuse, because the names of the stars aren't really that standardized. The constellations are now. We have 88 constellations that everybody can agree on. But then some cultures call this one Betelgeuse, but other ones don't. They may call it a different name. So because of that, what Bayer's designation was to say that when you look at a constellation and you're looking at the stars that are brighter than others, instead of eyeballing and saying, well, I think that star's brighter, now, and even in Bayer's day, the telescopes have light sensors in them and actually light meters. So they actually can measure the brightness of a star, and that's a really long physics topic on how it happens. But we just, for our sake here in the astronomy course, we know that light meters exist and that they're very useful in determining how much light is incident upon the meter. If you like photography, even if you don't like photography, if you use the camera that's on your phone, so it doesn't matter what level photographer you are, you know that a camera has a flash on it, right? So a lot of times when you take a picture, you're metering the amount of light that's incident on your camera lens. So when you're framing the photo before you actually snap the picture, you're looking at the picture and assessing, is something in the shadows? Can you see the whole thing? You may not consciously go through that thought process, but if you looked at the picture when you're getting ready to take it and you notice that something's shaded, you'll just naturally move your position and then until you can get a really clear picture you're happy with, and then you snap the picture. Well, a professional photographer carries around a light meter, and in our cell phones that light meter is already built in, but a professional photographer will want to gauge that at various spots. So if you're a professional photographer and you're photographing a person, there may be times when you want some of the person in the shade, and maybe you only want to highlight a particular feature of a person's face, and maybe you're all right with some of the area, a little bit of a a shadow elsewhere on the face or head or something like that. And maybe so you would actually want to take a light meter reading though, and once you figure out how much light is incident, you're going to set your camera's adjustments. Obviously, it's not on autofocus. You would have it on manual focus at this point, and you would manually adjust the settings on your camera to optimize the light coming from the one area of the face, but not where the shadow area is. You don't want to catch that. So the light meter tells you how to set your camera. Your cell phone automatically does it for you. But at any rate, those light meters are how astronomers can tell if a star is brighter than one, if one star is brighter than another. So when they're looking at Orion, astronomers were able to tell that Betelgeuse in the Orion constellation is actually brighter than Rigel. And so they're the two right here. Here's the two, Rigel and Betelgeuse in Orion. So the little light meter that's in their telescope, or that they use alongside their telescope, captured more light from Betelgeuse than it did from Rigel. And so consequently, the Betelgeuse is labeled Alpha, or named Alpha Orionis, and then Beta Orionis is Rigel. And so Alpha is the letter A, and Beta is the letter B. This one's Greek, and this one's Greek here. So it's using a Greek naming system, and typically it goes to 6 levels of brightness. And so that's really what you need to know here, that the common name Betelgeuse could be used in any constellation, but if we're specifically talking about Orionis, or Orion, then it's Alpha Orionis is actually the formal name or designation for Betelgeuse. And it's the brightest star in the Orion constellation, and that constellation is visible in the winter. But we'll actually get back to that. You don't have to memorize this chart. So another definition that we want to know when we're looking at the star or at the sky is that when we're looking at the sky, of course, we see the northern hemisphere, the sky in the northern hemisphere, and but the sky can be thought of. So we saw already the projection effect when it's looked at as a screen, but we know that that's not really accurate. But before we get into depth or depth perceptions, we do know now that stars are all at different distances and different depths and different distances from each other and from the Earth. So everything's really measured from the Earth. So we have the Earth right here, and then we have a distance to this star and a distance to this star. So we know that there's different distances and different depths. But still, no matter, though we know that, every time we look at the sky, though, they still all appear to lie on this celestial sphere. So that's what this is. That's what this picture is. This is the celestial sphere, and this is the northern celestial pole and the southern celestial pole. So here's the Earth. This is still Earth, and Earth is surrounded by this celestial sphere. So we live in the northern hemisphere. So America is here's the celestial equator right here, and that mirrors the Earth's equator. So America is in this northern hemisphere up here. So that's the sky that we see. We see the sky in the northern hemisphere, and so this whole ball here, that screen that looks like it, or what looks like the screen on which the stars are projected, that's actually called the celestial sphere, and it's the entire sky. It's the entire universe, or the entire sky, and there's 88 official constellations in that night sky, or in the entire celestial sphere. We don't see all 88 of them from the northern hemisphere, but we know that all told in the celestial sphere there's 88 constellations. And so again, the celestial sphere is another name for sky. And then but before we move on to the local sky, we're still in the celestial sphere, so we're still looking at the entire sky. And so there's designations or points of reference in the sky. And so the sky has a north celestial pole, and that equates. We have the north celestial pole. Pick my pen over here. The north celestial pole right here, and that's directly above the Earth's north pole. So again, here's the Earth. This is the Earth. And the Earth's north pole is directly in line with the sky or celestial sphere at North Pole, and the South Pole is directly lined up with the South Celestial Pole is directly above the Earth's South Pole. Or the text is above, we could say below, depend either way here. And then we have the celestial equator right here that is a projection of the Earth's equator into space. But then here, this ecliptic, that's our definition over here. The ecliptic is actually the sun's apparent, and I want to underline that, I'll get back to that, the sun's apparent path through the celestial sphere. So this is the apparent path of the sun. So why do I emphasize apparent? So I hope you're saying I emphasize that because the sun doesn't move. We revolve around the sun. So yes, that's the correct answer if that's what you said. The earth and consequently we on the earth revolve around the sun. But when we're on the earth, when we're on earth or when we go out and stand on our balcony or in our backyard, if we were to watch the sunrise, we would have to look east, and we would see that the sun rises in the east and sets in the west. So it's when we look at that, though, when we consider that sun rising in the east, setting in the west, we know, of course, it's due to the rotation of the Earth. But when we're standing on there, we feel like we're fixed and that the sun is what's actually moving. So that's why it's called an apparent path. It's apparent because the sun is actually fixed in outer space, and it's the Earth that rotates around the sun. But from the perspective of a human being on the planet Earth, it appears that it's the sun rising and setting. The sun rises in the east and sets in the west. So that pathway in the sky is called the ecliptic. So the ecliptic is actually the sun's apparent annual path around the celestial sphere, and it's the annual path too. So again, here's our definitions again. We have our North Pole directly above the Earth's north, South is directly above the Earth's South Pole, and then celestial. And the reason for above when we're referring to the South Pole is that if you were standing on the South Pole, the celestial pole would be above you. So that's really why we don't use the word below. We're talking from a reference point of you actually standing on the South Pole, standing on the Earth's South Pole, then the South Celestial Pole would be directly above you. And then the celestial equator is the projection of the Earth's equator onto the sky, where it mirrors that loop there. And this right here shows the Milky Way. This picture here shows a part of the Milky Way, and that's what we're going to look at next. So the Milky Way is the galaxy in which we live. And before I forget, these copyrights down here, whenever you see that, it means that this photo is copyrighted. And here's the copyright designation is Pearson, and these are all the copyright years. So it comes from a textbook published by Pearson. The pictures in the slides that don't have copyrights on them are actually from your textbook that you purchased, and so they're from the Cengage textbooks. So the Milky Way, again, the Milky Way is the constellation, or I'm sorry, not the constellation, the galaxy. It's the galaxy in which we live. So the Earth is in the galaxy, is in the Milky Way galaxy. And galaxy is a collection of constellations and or stars, collections of stars there. So in this picture here, when we talk about the Milky Way, we often use the term Milky Way in two different ways. In one way, it's the band of light. It's this band of light in the sky, but then we also use to talk about the Milky Way as being our galaxy. So here, this band of light, the band of light makes actually a circle around the celestial sphere. It makes a circle around the sky, and that's what this is. We're seeing a portion of it there. So. What exactly is that band of light, though? It's our view into the plane of our galaxy. So if we're standing here on Earth and we're looking up at the sky, we're seeing a little bit of our galaxy. And the way we're able to see that is that here, if we're looking down, if we were able to look down on the entire Milky Way galaxy, that's what it would look like here. That's what it would look like if we're looking down on the galaxy, or if we're standing up here and we're looking down on the galaxy. This whole picture right there, that's the Milky Way galaxy. And if we say the Earth is right here, we can look in a lot of different directions, and each direction we see a portion of that galaxy. If we look over here, we're looking a little deeper into it, we're looking below. So we're looking at a lot of pieces of that galaxy from any vantage point on the Earth. So when we look out, basically, since we're looking down, if we're up, if we were able to be above here in the in outer space, and we're looking at the Milky Way, this is the picture of the Milky Way, and it's in a flat plane. It's one-dimensional again. So much like that projection screen, if we were to be in outer space and we were looking down on the Milky Way, it would look as though it's being projected or overlaid on some flat plane or piece of paper. And the location of our solar system in the Milky Way is actually right here. So that's where the Earth is. And then when we look in any direction into that galaxy's plane, which are the blue arrows, we can see the stars and interstellar clouds that make up the Milky Way. So when we're on the Earth and we're looking in any of these directions in the blue, that's what we're seeing when we look in those directions. What we're seeing is this line right here, this band. We're looking at that band. So again, this band is what we see when we're on Earth. When we're on Earth here, and so here's the Earth right there. So there's the Earth, and then when we look in any of those blue directions, we're seeing a portion of the galaxy and of the Milky Way galaxy. It's that little band of light that goes through. When we look upwards here, we might see a little bit of dust or clouds in the sky from the Milky Way, but they're pretty sparse, and we're able to see through them, and then consequently further into outer space. So one question, given that last picture, would we be able to see with our naked eye another galaxy that lies in the same direction of our Milky Way center? So the same direction of our Milky Way center. So that's this here. Here's the center of the Milky Way. So if there was another galaxy in the same direction as the center, it's pretty much, being like an overlay on top of it. So would we actually be able to see if another galaxy were to lie in the same direction as our Milky Way center? Would we be able to actually see that? And so if you had a chance to take a look at these and read each choice here, the answer would be C. No, we would not be able to see it, and that's because because we're in the galaxy, the Milky Way galaxy, we're looking from the vantage point of being inside in the galaxy. So if there's another galaxy that lies in the same direction as the center of our Milky Way, it's overlaid right on. It's in the same exact direction. So it's moving over us, and but the clouds and intergalactic dust of the Milky Way would obscure our view beyond our own galaxy. We're only able to see our own galaxy. We would not be able to see any other galaxy that's in the same direction. But if it was perpendicular to our galaxy, we would be able to see that. We would actually be able to see it then, but not in the same direction. So how were stars named? Well, we sort of alluded to that already when we saw the alpha and the beta. They're named by a Greek letter according to their relative brightness within the constellation. So it may be the brightest one in that constellation. That's why it's relative, because when compared to a star in another constellation, it might be really light, or might not be as bright, or it could be vastly brighter. In its own constellation, it's going to be ranked. And so we saw Betelgeuse also already, which was the alpha, and then Rigel in Orion, both of them in Orion. Rigel was the second brightest, and it was given the letter beta. And actually it's alpha and beta. So I didn't. This is A and B, not alpha and beta. So alpha and beta is the correct designation, and that's what you see right here and right here. So a star's brightness is put onto a magnitude scale. So the brightest stars are first magnitude. They're the brightest, and the faintest to the unaided eye. So we're not using really a telescope here. Faintest to human sight, and the faintest stars are sixth magnitude in brightness. So the star's brightness ranges on a scale of 1 to 6, and that's the qualitative, a little more qualitative or a little more opinionated, whereas we're talking about the unaided unaided eye. But quantitatively, though, when you're using that light meter, a first magnitude star appears 100 times brighter than a sixth magnitude star, and a first magnitude difference gives a factor of about 2.5 in apparent brightness. But really, what that means is that you start out at larger magnitude. Which means that the larger, what you have is a larger magnitude number is a fainter object. So you start, and that seems counterintuitive. It seems like you're starting out with a really bright star, first magnitude, but what we're saying here, larger magnitude. That's this, a 6 magnitude, that's a larger number. 6 is greater than 1, obviously. So a larger magnitude, a number, the larger the number, the higher, bigger the number, the fainter the object. But how you can think about that, or how you can remember it, is consider this one first class. So everybody agrees first class is good, and this would be sixth class, and that would be like steerage. So the sixth class is, even though it's a bigger number, it's designating a fainter object. It's not as famous or popular, not as good as a first class star. So the scale of apparent magnitudes, we went from 1 to 6 in the last slide, but because of that light meter and technology getting better and better, think of how fast your cell phone gets obsolete. 2 years, you buy a cell phone now, 2 years from now they'll be better than what they are now. And so they get better and better. So these light meters, the technology was getting savvier and savvier, and we were able to see fainter and fainter stars. So that's what happened here. Here's our Hubble telescope. You probably all heard of that. It's one of the most potent or powerful telescopes, and it's actually out in space. And it was launched in space, and it's actually orbiting in space. And it's collecting all this imagery, collecting all these pictures of outer space and sending them back to Earth. And it's helping astronomers to be able to see stars that are really faint. And so this magnitude scale had to be extended. So here's our original with the naked eye, where our original is a 1 to a 6 is the original. So the fainter and fainter stars that were fainter than a 6, stars that were fainter than a 6 got numbered this way, the bigger number for fainter and fainter. But then brighter and brighter stars were also noticed. And then, of course, we have the moon and the sun over here in comparison. So the new scale goes all the way out to about -26. We had to extend it in each way. So again, the smaller the number, the brighter the star, just because when that scale was picked, they didn't know at the time that they were going to find even greater magnitude or smaller magnitude stars. And instead of coming up with a whole new magnitude scale, they just took the one they had and extended it. So magnitude and flux are a little different. The magnitude or brightness of a star is still subjective, but really what you're doing is in order to assign a brightness level to a star, you're collecting the flux. And flux means that it's the amount of light or light energy from a star that actually hits that sensor on your light meter. So you have a little light meter or light box. It's often called a light box, and it literally just looks like a box. And it has a little sensor over here. And then in here is all the electronics that make it work. And then there's a little reader over here that doesn't protrude out. It has a display screen. So actually, you can kind of think of it as your cell phone. So your camera up there with your cell phone, think of that as your light sensor. It's what's collecting the light that comes into it, and then there's a little reading up there that tells you, magnitude of 28 lumens. So luminosity, if you ever heard of that, luminosity is a brightness. On this scale, a 1 magnitude has a big range of luminosity numbers, and so would a 6, et cetera, and it's what you collect on this light box. So the light box is much thicker than your cell phone, though, and so about an inch thick, and a lot more electronics in there to process the light that impinges upon that sensor. So the light that hits the sensor is actually called flux, and the sensor is 1 square meter, or the collecting area of 1 square meter in 1 second. But 1 square meter, that's really big. That's gigantic. It's too big to fit in a light box. So the light box is scaled down. It's still proportional, but it's going to be a fraction of a meter. And so all this processing in there, all the electronics inside that light box are converting. They're taking the area of the sensor, and then they're expanding it out to 1 meter. So if they're collecting on 1/10 of a meter, then they're going to multiply by 10 and to get that 1 square meter. And so again, the flux is a way of determining brightness, and what the flux is a measure of light energy from the star on that collecting area or that light sensor. That's 1 square meter in 1 second. So the sky and the celestial motions, the sky above seems like a great big blue dome in the daytime sky and a sparkling ceiling at night. The first astronomers kept that in mind long ago as they tried to understand the universe, and but part of that observation, though, often they thought that the stars disappear from the sky during the day, but they don't. They don't actually go away. They don't actually set or anything like that. It's just that during the day the sun is shining, and because of the sun being the brightest of all, it obliterates the light coming from all the other stars, and that's why we don't see them. There's so much light in the atmosphere from the sky that we can no longer see the stars in the daytime. And then when it's not sunny but cloudy, the clouds are hiding everything. So we talked about the celestial sphere, and again, just a reminder that celestial sphere would be the whole entire sky, irregardless of the hemisphere that you live in. So that's be like if we took this little bubble right here, we made it an entire balloon, and that would be the whole celestial sky again. But we live in the northern hemisphere, and we're only going to see the sky in the northern hemisphere, and so that's the local sky. If you lived in the southern hemisphere, you would only see the southern part of the celestial sphere, and that would be your local sky. We can get even more granular and say, well, we live in Philadelphia, and in Philly, most of we may not be able to see every star as clear as somebody in Seattle could. Because let's just say that Philadelphia is right here, and we're able to see like all that sky, and Seattle is over here. So they're going to have a real hard time seeing this one. Just going to appear seeing a star over there because it's going to appear so much farther away than where they're at. So that too is another example of a local sky. And the object, and here object. Oftentimes we use the word object or the word body, and so object or body, either of those is whatever they indicate whatever you're looking at. So if you're looking at a star, we're calling the star an object or body. It could be an asteroid, it could be the moon, it could be another planet. So object and body are interchangeable words for the astronomical item that we're interested in or that we're observing. So the object that we're observing has an altitude, and it's a distance above the horizon. And then it has a direction too, and the direction's along the horizon. So that altitude and direction specify the location of that object in your local sky. And then the meridian is a line that passes through the zenith of the local sky, and it connects the north and south points along that horizon. So, so here's your horizon. Actually, let me erase a little bit. Let me erase here. So your horizon is really what you're standing on. So, so this right here is your horizon. That's what you're standing on. That's your boundary. And then you're looking at your local sky. So this part of the celestial sphere is the northern hemisphere, and it's your local sky. And then the highest point right there is your zenith, and it's at an altitude of 90 degrees. And then right here is the part of the sky that's an altitude of 60 degrees, and its direction is southeast. So we already marked east right here and north, so that means south is down here, and then of course west. So our little axes are here. But what's really important though in determining that 60 degrees is that this is you standing on the Earth right there. So this is you, and you're looking along that zenith right here, and then here's your position. So you're in. If you think back to your math class, in math you always have a coordinate system, right? So you're standing at the origin, and you're looking directly up at your zenith. But now, so that's your 90 degrees. That's your 90 degree angle, and then you end up with you're going to turn and you're going to look in a little different of a direction. So when you're standing on Earth, and so now, so we see you pointing your arm out right here. So your arm, and your arm right there is basically right along that line right here, and you're looking at that star right there. So you want to know the altitude of it, and so you're going to draw that plane. This would be your x direction and your y direction right there. Well, the angle is always made with reference to that x direction. So your x direction, it's not the east or the south. It's just somewhere in between in this case right here. So you got to make this directly. And if you looked up, and you would want to bring this down. So make your triangle right there. So here's your 90 degree triangle, and your angle is always with the horizontal. And the horizontal, for astronomy, is the direction that you're standing, pointing to that star. So here's your arm pointing to the star right there, and then here's your horizontal, and then you connect them to make that right triangle. And then you can use your trigonometry you can extrapolate a distance here and a distance here, and then your opposite over, this is the opposite side over the adjacent side, make that calculation. In this case, it gives you a 60 degree angle. And we're not going to get into actually doing those calculations. So what you need to know for this class is that the altitude is measured above the horizontal, and it's measured in degrees. It's not a distance. It's not like you can take a ruler and go ahead and measure all the sides, or measure from the Earth up to the star. You can't do that. So distance and direction are direction actually is a little more subjective, southeast, kind of thing, or northeast, northwest. But the altitude is going to be a number, and it's going to be given to you in degrees. And then again, that meridian is the line that passes through the zenith right there and connects the north and the south. And so that's going to be your frame of reference too. Here you are in this picture. You're not looking entirely south or entirely east. You're looking at some combination. So that's the line you get right there, and then you calculate the angle to it. So some more terms here. Zenith is the point on the celestial sphere directly overhead. Nadir is the point on the celestial sphere that's directly underneath. And then the celestial equator is the projection of the Earth's equator on the sphere. Northern celestial pole is the Earth's north pole projected onto the celestial sphere. And here we go. Here we see these again, where we see the Earth. We see the Earth. Here's the Earth's. Here's the Earth's axis right here. So we get the South Pole and the North Pole, and then our westerly right there, and the sun's path in the celestial sphere is it sets in the west and rises in the east. So that's what's going on here. Here's the east, and we're rising in the east and rising, and then we're set in the west. So that's the ecliptic. The ecliptic again is the path of the sun through the celestial sphere, and then we see, of course, the horizontal right here. The horizontal part is actually not quite once it tips like that. It's not once the Earth goes on that little angle. It's at an angle again to that that equator that's projected onto the sphere. So the celestial sphere again is the entire sky. But the distance between two stars on the celestial sphere can only be given as a difference between the directions, between the degrees that are now calculated. Like this picture shows you, and it just shows you pointing your arm. But that's really the technology is really good now that astronomers are actually able to calculate the degree of difference between two stars, and so their distances on the sphere are consequently measured in angles, and so the 360 degrees is a full circle, and then we have an arc minute is 1 degree, and that's equal to 60 feet, and then the second here is equal to 60 inches, and arc seconds. So mathematical terms here for calculating, but again, what you need to know is that the difference between two stars, or the distance between two stars on the celestial sphere can only be given as the difference between their directions, and it's an angular displacement, so it'll be measured in degrees. So the celestial south pole is not visible from the northern hemisphere. So that means we cannot see the celestial south pole. So any of the constellations in the celestial south pole, we cannot see. So we're in the northern hemisphere. So Hemi is, Hemi means half. And half, and then sphere is not a round object, it's spherical, so it's going to be more elliptical or spherical, and we have two of these, and so really if we thought of it in 3D, like that little bubble out there, and then this one here, so we have two spheres right there, and if we took this round globe and just opened it up, so this yellow picture right here, we can take that and fold it into a circle, or fold it to look like a globe. And we would, but really what's important on this picture before we even fold it up is that more than about 90% of the population on Earth lives in the northern hemisphere. That's because most of the land masses are in the northern hemisphere. So here's the dividing line right here, the equator. So this is the equator, this is the northern hemisphere, and this is the southern hemisphere. So cross this off. When I cropped the picture, I should have cut that out. That's the northern hemisphere being down here is just saying that the area highlighted in yellow is the northern hemisphere. So again, the northern hemisphere is this yellow part. Southern hemisphere is the part down here that's not in yellow. So that's the southern hemisphere. And again, we here in America, it doesn't matter if you live in Florida or Maine, doesn't matter, or even Alaska, or Hawaii down here, does not matter. No matter where we are on Earth, we cannot see the southern hemisphere. We cannot see the sky or the stars in the southern hemisphere, and that's because The equator, that's our horizon. And so anything below the horizon down here, we can't see it. So our hemisphere is this one right there. And this is our local sky, and nothing in the sky there is visible to us. So measuring distance again across the sky, you start out with a latitude of 90 degrees. So our Earth, or the Earth is lined up right here. The Earth is lined up right there, right through the zenith. So that's a latitude of 90 degrees. But then when you take this, when you take this, the ring or the path of the when the path of the so actually this is north right there, and this is east right here. But then when you take that and you rotate it and you put east right here. So if we put the North Pole right there, we move east over here. This path of the sky, the ecliptic, here's the or here's east. Sun rises in the east and sets in the west. So we end up in this configuration when the Earth turns this way. We're actually at a latitude of 0. And then when the Earth is tilting this way, it's a latitude of 30, and then a negative 30 when tilted in the other direction, or tilted in 30 degrees in the opposite direction. So again, that involves the direction or the orientation of the pole. So when we have the South Pole right here, and we're in this line right here, it's actually a latitude of 30 degrees above this horizontal over here. So the apparent motion, again, we're using the apparent because it looks like the sky is moving. We're so used to standing on Earth and not feeling like we're moving or not feeling the Earth's rotation, but in reality, again, it is the Earth that's moving. But when we're standing on the Earth and we're looking north, we'll see stars that appear to be circling counterclockwise around that North Pole, and that's because our rotation is the opposite. Our rotation is one way, but it makes it look like the sky is rotating against us. And then this one's a really important slide right here, more important than the last one. This one, the circumpolar circle, is a circle or some constellations that are located around the celestial North Pole. Well, those constellations never set below the horizon, so they never go below that horizontal. And because they never go below the horizontal, they're visible every night of the year to everyone in the northern hemisphere. Polaris is one example. It's called the North Star or the Pole Star. But it's famous for holding nearly still in our sky while everything else moves around it or revolves around it. So the rotation of the Earth now comes into play is a lot more important because it feels like all that motion and revolution around the axis or around the axis makes that celestial sphere move, and but some of them are fixed, and the ones that are fixed in the sky that are there year round are shown in this picture, are shown in the picture right here. So this picture, this is the North Pole, and consequently Polaris is called the North Star or the Pole Star, and it's famous for holding nearly still in our sky while everything else rotates around it, and while the northern sky actually moves around it. South of the equator, Polaris drops out of the sky. So if you move to a location south of the equator, you would not be able to see Polaris. It's in the uppermost or the zenith of the northern hemisphere. And but in the southern sky, there's nothing comparable to the Polaris star. If you're in south of the equator and you're looking at the sky, you're not going to see an equivalent to Polaris. So the apparent motion of the celestial sphere, again, depends on which way you're viewing it. Here, if we look south, we get, if we look south here, the first picture, it looks like we would see stars moving actually to the right or to the west. The right would be west in this case here. So here's if we're looking south, if I'm sorry, if we're looking southwards here. It looks like they're moving north. That should be north. Yeah. So this one should be north right here. If you're looking south, they appear to be moving north. If you're looking east, as shown in this picture, you'll see stars rising and moving to the upper right. So they're going to the upper right, would be south. So if you're going east, you're looking east, upper right would be south. Down here would be north, and then west over here. And then if you're looking south, you see stars moving to the right, or in some cases westwardly. And it's a little hard. That's a little objective to really tell. Again, this is just for your opinion, or just for your edification. This would not be a test item, but the point that you want to take away from this is that the motion of the celestial sphere again is apparent. It's because the changes in the sky come as a result of the rotation of the Earth on its axis, and that rotation will tell us the orientation and how. But no matter how or what that orientation is, it though we're moving, it appears as though it's the sky that's moving. So scientific models give us the celestial sphere, and they're carefully devised conceptions of how something works, but we can have idealized models, and so in that case, some kind of complex aspect can be simplified or omitted. And so it's kind of like when we talk about the universe as a ball and stick model of a molecule. It doesn't, or actually, if we, before we even get to the astronomy part, if we use a ball and stick model of a molecule, it doesn't show the strength of the chemical bondings. Like a water molecule is H2O, so we can draw two hydrogens and put them on a stick, so they're both hydrogens, and then set H2O, and then we have our oxygen over here, and but we're not really, like if we did this ball and stick model, we're not seeing the strength of the bond here, or when they bond, when the two hydrogens bond with that oxygen. We're not the ball and stick model doesn't really show it, but it's good enough. I mean, you get the point here that you have two hydrogens and one oxygen, so H2O. So it's a simplification that's omitting something like the strength of the bonding between them. And obviously, if you're studying chemistry, that's going to be really important. What you want to remember, though, is there's limitations on every kind of model, and the same is true here for that celestial sphere, because the model makes it look like everything is still projected on a screen, even though when we try to show the depth of that, we still wind up with an oversimplification of the model. So some common misconceptions. The stars are not in the sky during the daytime. Truth is that the stars are actually there during the day and the night as well. They're just not visible during the day because of the brightness of the sun. Another misconception is that Polaris is the brightest star in the sky. It's actually the 50th visually brightest, but it's important because of its position, not because of its brightness. Polaris is the star in the northern at the North Pole, so it's often either the North Star, often called either the North Star or the Pole Star, and it appears to stay fixed there. It doesn't ever appear to move, so you can often navigate by looking at that star, navigate your way north by keeping your eye on Polaris. So another really important definition here is precession, and this is the one that's important for astrology, in understanding astrology and zodiac signs. So precession, though, is actually the result of wobbling of the Earth's axis of rotation around that vertical with respect to the ecliptic. And it takes about 26,000 years to make one 360-degree rotation about that axis. We have the Earth, and let me get my pen out here. So we have the Earth right here, and the Earth is rotating about its axis. So we have Earth, and then Earth's axis right here. But it's not like a perfect top. So if you have that toy, a little toy top, and you spin it, it spins really good on that point. But eventually it slows down and it starts to wobble. It starts to wobble this way and it starts to wobble that way. So it does a little wobbling back and forth, even as it's spinning. So it wobbles this way, wobbles that way. So that's what's happening here. The Earth's axis is not pinned to any kind of mat or anything like that. We know that. And when we look in the sky, the planet looks like little fireballs, just like stars do. And so we know it's not firmly affixed. But its rotation, though, instead of going completely around this way, it goes at a rotation there. So that means this axis of rotation is off. It's about 24.5 degrees off of this northern off of this latitude here, not the horizon. Horizon's this way. It's the latitude right here, so it's about 24.5 degrees off, or 23.5 degrees out that way. Or I'm sorry, it's right under my nose right here. 23.4 degrees is that angular distance off of that fixed axis. So if we took the Earth and we put this axis right straight through it, it's actually tilted 23.4 degrees, and we see the Earth's orbit in this plane right there. It's orbiting that way, and so as it orbits, though, this part wobbles. This part wobbles, and then that wobbling also causes a little bit of a change as it comes around here. So the Earth's axis of rotation wobbles a little bit around that vertical, and that's this part right here. So this line is the vertical. So we're 23.4 degrees off the vertical, and then this this axis right here with this wobble, it's going to rotate or wobble around that vertical, and it takes 26,000 years to make one 360-degree loop to complete that circle once. So it takes about 26,000 years to complete that, to complete this circle, to wobble around this circle. That's one circle. One circle's 360 degrees, and it takes 26,000 years to complete that 360-degree loop. So the Earth's rotation on its axis is what causes the cycle of day and night, but its motion or revolution around the sun defines a year. So rotation is defined as the turning of a body or object on its axis, and revolution is revolving that body around something. So axis is internal, and so you have your sun right here, and that's the axis. Oh, my drawing is terrible. Let's try that again here. So we have the Earth, and then the axis goes through the Earth right there, and we have a rotation around it that way. But then revolution is the motion of the body, any body or object, not the physical human body, the object that we're talking about. Motion of that object around the point outside of the body. So here the axis is within the body. So the axis is within the body. But then when we have the sun, we have the sun here, and the Earth. Well, the Earth revolves. Earth revolves around the sun, and it rotates about its axis. Rotates about the axis, revolves around the sun. So the axis is within it goes through a point inside the body, but revolution is moving around that body, or moving around the point that's outside to that body. So this is the point that we're revolving around, and it's external to the Earth. So the Earth's rotation causes day and night. It's rotating around the sun, but it's it's revolving around the sun at the same time it rotates on its axis. So when part of the planet is exposed to the sunlight, then we have daytime, and the other side of the planet has midnight, and then we see sunset and sunrise down here, so the Earth, here's the Earth's rotation is going to be this way, and here this part is facing the sunlight, and consequently is daytime, and then nighttime here and daytime here. And so the sun's apparent path on the sky, that's the ecliptic. We did mention that before. And here's what we see right here. This is the ecliptic right here. And then Kepler's law says that as you rotate around the sun, you're going to move to different points. And each time you sweep out that same amount of area right there through here, those parameters are all the same. But aside from Kepler's laws, as you're rotating and revolving, your view from Earth on January 1st is different from your view on March 1st and further on down the line until you get back to January 1st. That those views are going to change. And then so will our seasons. So the Earth's axis of rotation is inclined by 23.4 degrees, and that inclination is what causes the seasons. So the Earth's axis of rotation again is inclined by 23.4 degrees, and that's what actually causes the seasons. So if we look here, so again, here's our 23 degrees of rotation right there, and it's not that the physical object of the Earth is actually closer to the sun. It's the inclination that causes seasons. If the Earth was on that axis right there, everywhere on Earth would feel the same amount of radiation. So here's in this picture the sunlight over here is nearly direct on the northern latitudes. So here's our latitude lines. There's the equator, and so this is a northern latitude and this is a southern latitude. So up north, the sunlight's nearly direct on the northern latitudes right here, and then but then down here, this last one, we see that curve. Let me erase that. See this line right there? That line right there compared to down here? So that's direct sunlight. But then down here you get direct sunlight there, not so direct. It's skipping out. This part's not even hitting the Earth right there. It's skipping it. So locations down here are going to be cold. They're not getting as much sunlight. Now here's direct sunlight, same thing right here. But then it's colder up here and colder up here. Not as much light. Remember that flux? In this ray, this beam right there, a little bit more flows onto the Earth, but a lot of it skips the Earth, misses it, goes right over the top. Same thing down there. So, a common misconception is that seasons are caused by the Earth moving closer to or farther from the sun. The truth is that the seasons arise because of the Earth's axis. That axis of rotation is not perpendicular to the orbit. So let's go back and look at that. Here's the axis of rotation. Here's the axis of rotation, and it goes this way. So it's orbiting that way. If it was perpendicular to the orbit, see right there, this is perpendicular now. This is at an angle of 23.4. If it was perpendicular, everybody would get the same amount of sunlight impinging upon it. But when you tilt it, some areas, the northern and southernmost areas, don't get a lot of light at that, don't get the sun. They don't get that energy or heat. Some of the energy or heat goes right over the earth. It doesn't even touch the earth. So when it goes by like that, you don't get as much flux. So in January, the Earth is actually 1.7% closer to the sun than the average orbital distance, but that's actually negligible. That's such a small number that it doesn't mean anything. It doesn't change the amount of flux because the sun is so big and so bright that the one tiny little percentage like that's minuscule. So let's talk about these. Oh boy, I hope that slide came through. It did. I'm sorry, I must have another chart in there. Or a blank slide actually. So that angle of incidence, that angle, that tilting when you get, so let's draw the picture here. So here's our grid. Remember in your math class, this is X and this is Y. Well, here's the axis of rotation. And that's that 24 or 34.4. But then here's the Earth. And then some of the sun goes over and below, and then you start hitting it at various different degrees. So that looks like this little cone right here. So the summer solstice, during the summer solstice, the light, the angle, we're still angled there, but the rotation, you're kind of coming in. Well, you're rotating a little. You're still rotating at that point, but most of the places on the northern hemisphere are mostly directly hitting that sunlight. But the winter solstice, we're a little lower. Our angle or approach with the sun, it has less rays or incident on it. So we tend to think of the sun being a little higher in the sky or further away, but it's not really that. Again, it's that the summer solstice part has, if we go back to this picture here. So the summer solstice part, it puts America, or the eastern Philadelphia part, really like directly right here. It puts it more directly in that position, and but then in the winter, we're just slightly a little bit more up in the layer like that. Less sunlight is hitting, and it's part of that path, that elliptical orbit around the sun. So in this area right here, we're not closer to the sun, and I drew that out of scale. We're not ever closer or farther away. We're all these are equally distant, but that when we've moved as we're revolving around the sun, when we revolve here, we might be in the summer solstice right here, and then winter solstice right there, and so as we spin on that side, we in the summer we get more of the light out of this range and impinging on the Earth, and in the winter it's not as direct. That angle with the angle of the sun with the Earth or position is we end up seeing the light on the Earth being a little more scattered than we would expect it to be. And so in the one picture, we saw the sun on this side hitting it, and then in this picture here, now we've rotated to the other side of the sun, and so in this case here, if let's take this point right here. So here's the equator. We can't really see America too well here, but it's right about here. So in this case right here, sunlight is spread out on the northern latitudes. It's just scattering a little more. So we're going to see winter in this case. But then when we were over here, we're actually more in this spot. So if we're down here. So if we drew that line when we're on this side, and the sun was over here, we got much more of the direct sunlight there. So it's because the angle is in the winter. The angle positions America away from the sun, not farther distance wise. It's just positionally angled away from the sun. And then in summer, the summer solstice, we're angled toward the sun. So being angled toward the sun gives us much more direct sunlight. So let me get back to that picture again. And so back to this picture here. I don't think it lets me. Yes, so back to this picture here. If we can see a little bit, we can see America right in here. So America is angled toward the sun. It's really close to the sun here. So this would be the summer solstice or summer, and we're directly in the path of the heat of the sun. But in the winter, we're angled away. We're angled away from the sun. So in the winter, here's America. Here's America. Here's America right here. So we're not directly in the line of the sun right there. We're angled a little more away from it. So this would be like the center. This is the center. Let me erase this here. So we're going to the sun. This part says to the sun right here. So so this is really to the center of the sun. But America is up here now. And whereas in the summer, we're right here. So we're right in that direct path of the heat, the most intense part of the sunlight. And up here, it's more scattered. So we have winter in that position and summer in this position here. And so here, the Earth at the winter, or at the northern hemisphere, we were in the winter, and we're not getting a whole lot of sunlight in its position, and not a lot of sun. And then the northern latitudes, again, it's all spread out. Everything's all spread out. Light's all spread out. So the motion of all the planets are obviously around the sun, but then Earth has an orbit right here. This is the Earth right here, and then Venus and Mercury are within the orbit of the Earth. So we can see Venus and Mercury pretty good with the naked eye. And so at sunset, when the sun sets, you want to look west, and you should be able to see Mercury. You should be able to see Mercury right in there, right in the beautiful colors of the sky. So it hasn't turned to dusk yet. We're still seeing these colors, and you should see Mercury pretty good. And then at sunrise, we want to look east, and we can see Mercury again in the colored pattern, the bright part. Similarly, up here, we can see Venus in the twilight area, twilight zone. And over here, we're getting there. It's in a little darker of a hue, a little further out from the sun. But we're able to see Mercury and Venus close to the sun because they're within the orbit of the Earth. So astronomical or astronomy's influence on the Earth's climate are due to three things: the eccentricity of the Earth's orbit, precession, and the inclination of the Earth's axis. So eccentricity of the Earth's orbit is that the Earth's orbit around the sun varies from 0 to 3% over a period of approximately 100,000 years. So anywhere that the Earth is in that percent change, where the orbit changes a little bit, it contributes to climate changes. Precession, that wobble of the Earth that takes 26,000 years to form a rotation, like one complete spin or wobble on its axis. And then the inclination, that currently we're inclined 23.4 degrees, but that inclination varies between 22 and 25 degrees over 41,000 years. So all three of those together contribute for climate change and some pretty drastic changes. We see ice ages and predominant, but that's actually the predominant form. We're still in an ice age because the polar caps have ice on them. When we're not in an ice age, there's no ice on the caps. So so because we're still in an ice age that's receding, glaciers are going to recede as well. But again, the astronomical influences, these three things, these are the three factors that are due to astronomy and the astronomy's effect on the climate. They're not alone. They're not the only things. Of course, our behavior leads to climate change too, and but we're going to focus just on the astronomy part. And so the three factors are eccentricity, precession, and inclination. And the astronomer Milankovitch, he hypothesized that all three of these aspects are responsible for long-term global climate change, not just wildly fluctuating temperatures. Like if you saw the temperatures over the weekend in Denver, it was 90 degrees, I think, on Sunday, and then Monday they had a really big snowstorm. So it was like a 50 to 70 degree drop in temperature overnight. And that's not really due to astronomy, anything like that. The astronomy changes are a very long term. I mean, literally, we're talking hundreds of thousands of years here notice any appreciable changes in temperature. So back to astronomy and astrology. So astrology in ancient cultures, back in ancient cultures, astrology and astronomy were pretty much the same thing. In ancient cultures, the people believed that the planets and their motions influenced the fortunes of kings and their nations. And that was the period, the Babylonian period. They were typically the first to begin studying astronomy, studying the stars and the planets. And to them, the planets and the stars represented any of the multitudes of gods that they worshiped. And then the Greeks took it a step further and said that it's not really just kings and nations. They're not really privileged. The Babylonians tended to think kings and nations were so privileged that the gods looked more favorably on kings, and consequently, if the gods favored a king, they would favor his nation, and that the whole nation would prosper and rise and fall in tune with the popularity of the king. And if the king remained in the good graces of the god, so would the nation. But the Greeks thought it was much more personal than that, and the Greeks felt that the planets and the motion of the planets actually influenced every individual. It didn't matter if you were a king or not, and it didn't matter, according to the Greeks, it didn't matter whether the gods favored or did not favor a king. They basically felt that each individual, that individual's personality and that individual's fortune was affected by the sun, moon, and planets at the moment of birth. So when you were born, the instant in time that you were born, the Greeks believed that moment defined your personality and your fortune. And that belief is known as natal astrology. And it still is in effect today. It's not quite a religion like it used to be, and maybe there are some astrologers that still worship a particular god, other than the Christian God or the Jewish God or any god of religion. But the natal astrology there may be a god of heaven or something like that. That's not in a Muslim or Jewish or Christian or a Bible commonly associated with any religion. The astrology is not affected that way, but the book that they would worship or that holds not worship, but the book that is their treatise or guideline is Ptolemy's treatise on astrology. And it was he who wrote all about your personality type and being lined with the stars in the sky. and that your birth moment, the sign that you're born into, is indicative of your personality and your likelihood to succeed. And there's apparently in Ptolemy's treatise a whole lot of factors that are associated with a person maybe born in Capricorn versus a person born in the Libra sign. Libra tends to be, that's the scales, and the thought is that anybody born in that sign is very justice oriented, very fair minded. And so all of that was spelled out in Ptolemy's treatise. That's the Bible of the astrologers. That's basically their playbook, or the principles that they live by, and Ptolemy's treatise is the key foundation for your horoscope, or for horoscopes in general. So the word horoscope comes from the meaning, it comes from the Greek terms hora, meaning time, and scopus, meaning watcher or marker. So the word horoscope actually means marker of the hour, and so your sign is in the zodiac, and the zodiac is the belt of the sky within about I'm sorry, this should be 8 degrees. That's not an 80. Well, that didn't come out right in my Explain Everything app. So that should be 8 degrees. So the zodiac is the belt of the sky located within about 8 degrees of either side of the ecliptic. Either side of the ecliptic. So the ecliptic is, so if this is the Earth, and the path of the sun around the Earth. So if this is the ecliptic right here, here's 8 degrees over here, and here's 8 degrees over here. So the zodiac is the belt of the sky within about 8 degrees of either side of the ecliptic. And it includes the sun, the moon, and the planets. And then it's divided into 12 equal divisions. Divide that into 12 divisions. And again, that should be 30 degrees. Each division is 30 degrees long. That is 30 degrees this way, right there, 30 degrees long. And then, so the sky is divided, or this belt is divided into 12 equal divisions or signs, and each is 30 degrees long. So the signs are what we know today as your sign, whether you're Libra, Capricorn, Scorpio, all the astrologic signs are those 12 divisions. And each sign's named after a constellation in the sky through which the sun, moon, and planets were seen to pass at the moment you were born. So your sign is the zodiac sign in which the sun was actually at the moment you were born. So we can look at the sun, moon, and planets as falling in a particular zodiac, but it's more precisely the sun itself. So if the sun was in Libra when you were born, you were born September 23rd to I forget what date in October it ends. But so if your birthday is in that range, or if you're born that day, you are born into this sign of Libra. So right now we're in Virgo. Up until the 23rd of September. So 22nd of September is the last day of the zodiac sign Virgo, and then we go into Libra, and so all that sounds well and fine, but Ptolemy wrote his treatise more than 2,000 years ago, and that's when the signs were all named. But due to precession, the zodiac constellations are shifting west along that ecliptic, going once around the sky every 26,000 years. So we can figure that 26,000 years or 2,000 years ago, a little more than that, was when the zodiac was named. So the 26,000 years it takes to go, so the Earth or the sun, so if we're, let's just start back over again. So say we're in Virgo now. So if you were born in Virgo 2,000 years ago, though, that would have been correct. But now 2,000 years out of this 26,000 year period has elapsed. So we got 24,000 years ago before the sun is back into that same sign. So you were born, we all were born fairly recently. And so we're still, all of us can say that our sign is actually shifted about a twelfth of the zodiac. So, for example, my birthday is September 24, so I'm a Libra, but 2,000 years or more have passed since Libra was assigned, since the sun was in Libra. So in reality, I was born in Virgo, so everything shifted west a little bit. So your sign is one before your current sign. So me, with my birthday being the 24th of September, that would put me in Libra, according to the newspaper. When you see the horoscopes in the newspaper, it always puts the dates in there. But in reality, since we're a 12th into this 26,000 year precession timeline, I'm actually a Virgo. So you're, if you look in the newspaper at all the zodiac and you find your sign, the one before you is actually your true sign. So what is the difference between astronomy and astrology? Well, that depends on the definition of a scientific argument. So an argument is a summary of evidence and principles leading to a conclusion. So that's what lawyers do. Lawyers have their opening statement and their closing argument. So their closing argument is a summary of all the evidence and principles, and their conclusion is whether the person's guilty or not guilty. And well, they want to lead you to that. The lawyer won't say it. They want you to conclude that they want you, the jury, to conclude that a person's guilty or innocent. So a good scientific argument has a hypothesis, and that's basically an explanation for what happened, and or what you think is the fact. And then you're going to describe all your observations and/or your experiments that support or deny that hypothesis. So other evidence and alternate explanations can certainly come to play, but your good scientific argument is all fact-based. You have your observations, your experiments, other evidence, and you're collecting a whole lot of data on the topic. So that's what astronomy is. We have ways to measure brightness. We can measure distance through angles. We know that the sun is the center of the universe, and that, or at least in our solar system, and that planets revolve around the sun. We know that they revolve around the sun and that they rotate about their own axis. So astronomy is very much a science. It's very mathematical and very proof-oriented. But astrology is a pseudoscience. It's not really a science, and so pseudoscience is a set of beliefs, to include scientific ideas, but it don't follow the basic rules of science. So a pseudoscience is making an assertion, but it's not really following any of the rules of science. There's no experiments being done. It's just really an opinion. So when you read your horoscope, that's just an opinion. I mean, that's not a real fact about how your day is going to go. I mean, of course, they could tell you to play a lucky number, and you may not. If you played those numbers, you chances are you won't win. But pseudoscience is not scientific based. Science. A scientific claim, you can test it and verify it. There's a way of testing something, and the results of your test will tell you if the scientific claim is true or not. Like vitamin A is, or I think it's A, is good for your eyes. Maybe that's the scientific claim, but you can test and verify whether long-term use of that vitamin actually improves your eye. Glucosamine chondroitin is the one that's supposed to be really good for your knees. You can take that for a year and decide for yourself if it really improved the health of your knee. So you can do a scientific study. You could test something and verify it. But with astrology, it's really a pseudoscience. There's no connection between the positions of the sun, moon, and planets and people's personalities or the events in their lives. There's no connection to say when there's a full moon out there, we all act battier than hell. That's an opinion. There's no proof to say how the full moon really affects your personality, and it certainly doesn't affect the events in your life. Are you going to have a successful semester? Doesn't that There's no connection between what sign you were born in and whether you're going to whether you're going to have a successful semester or a lousy semester. So no connection again between the sun, moon, and planets with your personality or events in your life. So if you have any questions, please do feel free to email me, and I'll try to get back to you within 24 hours. So thank you, and see you at the next lecture, or, well, we'll talk to you at the next lecture.